All right. Hello, everyone. This video is gonna cover BVP 13 in light of your final that's coming up. So yeah, I think this is an important problem, and it's not the most trivial one. So it should be interesting for you guys. Basically, we're gonna be looking to find the steady state temperature distribution in the region below. As always, steady state temperature distribution right away just implies Laplace's equation here. So in this case, we're looking at Laplace's equation in polar coordinates, because obviously we have an annular region here, I guess a semi-annular region. We have inner radius 1, outer radius b, and we have theta 0 here all the way to theta equals pi on this side. So yeah, and then we're given obviously the following boundary conditions. Phi of r0 is 0, as we see here. This side is fixed at 0. Phi of 1 theta is equal to 0. So throughout the inner radius here, temperature is held at 0. Same on the outer radius. Phi of b theta is 0. So outer radius always 0. And then at the left side here, we have phi of r pi is equal to f of r. So it's just some function of r for this side of the annular region. Now, yeah, we're given essentially homogeneous boundary conditions here. So we're able to just use the separation of variables and go through with it. So we're going to start that off. Let phi equal to some big function r of r times some function big M of theta. We're going to go ahead and plug that into the polar form of Laplace's equation, which is right here. The polar form is just 1 over r d over dr of r d phi dr plus 1 over r squared d squared phi over d theta squared. So yeah, like I said, if you guys have seen the last video, these formulations that are like different coordinate systems for Laplace's equation or whatever it might be, they're important to know, and I think there is a useful info sheet, so maybe some of them are given on there, but I would definitely check, and if they're not, try your best to remember those, because if you can't get this right off the bat, you're pretty much stuck for the entire problem, and it's going to be tough to even get any part marks. So definitely be aware of that, and double check the useful info sheet. Make sure everything you need is on there. Otherwise, try your best to remember. Anyway, we're going to plug in phi into this right here. And we'll just, like we always do, rewrite that. We have M over R, D over dr of R, D big R of R, plus R over R squared, D squared M over D theta squared is equal to 0. We're actually going to multiply it through here by r squared over rm. Usually we just do 1 over rm, but since we have the polar coordinates here, it'll simplify this a little bit and give us a more relevant form. So we actually get r over big R, d over dr, r d big R dr, plus, I believe this is, just want to make sure I don't make a mistake here. This will just be 1 over m, d squared m, d theta squared is equal to 0. Straightforward enough. We're going to move this to the other side, get our eigenvalue equations here. dr is equal to -1 over m, d squared m, d theta squared is equal to some constant lambda. This isn't new, hopefully. Just equating that to lambda is how we do our separation variables essentially every time. Now we can actually look at the left-hand side here and consider that we might be able to solve this. The right-hand side obviously looks pretty trivial, but we actually wouldn't be able to use that, given that the left-hand side is much more complex. So we're going to start off with the left side. We're going to write r over r, d over dr of r dr dr is equal to lambda. And we're going to compare that to, we're going to try to write that in SL form essentially. That's just going to be done pretty simply by bringing our r over r to the other side here. We get r dr dr is equal to lambda r over r. Now, important to check here is that we do have homogeneous SL conditions. So we have r of 1 is equal to 0, and r of b is equal to 0. Again, that's just our boundary conditions here. We have the radius, the inner radius is held at 0, outer radius held at 0. So we do have homogeneous Sturm-Liouville conditions here. And as always, what that implies is that the eigenfunctions are orthogonal with respect to the weight function W. In this case, 1 over r, as we can see here. If you guys aren't familiar with this stuff, like really just writing out the Sturm-Liouville form and solving for the weight function and stuff, checking the boundary conditions, definitely recommend you review that, because it's very important and comes up in a few of the BVPs. So really having that down, knowing exactly what the Sturm-Liouville form looks like. In this case, we wrote it like this, but there's a couple other ways you can write it. But really important to be able to recognize that. So review that well if you're not too familiar with it. But anyway, I'm going to keep going now. Given this, obviously we just have r dr minus lambda r is equal to 0. We can write that if we just apply the product rule here, we get r squared d squared r over dr squared plus r dr over dr minus lambda r is equal to 0. And so this is actually an Euler equation, which is another important equation that you kind of need to know how to solve. This is essentially from ODEs, so hopefully you recall a bit of that, and it has been applied a couple times throughout the course. But anyway, this is solved by just letting r equal r to the k. Sorry about that. And plug in that into the equation essentially. And all we get is that k times k minus 1 plus k minus lambda times r to the k is equal to 0. We can divide through by this, obviously, since the exponential won't be 0, to get that k squared minus lambda is equal to 0. Hopefully that was trivial here. Basically, we're just multiplying through here, and then we get negative k plus k is 0. And this is what we get. And then obviously this implies that k is equal to plus or minus square root of lambda. Now, with that given, we can go ahead and plug that into to this right here. So we had r is equal to r to the k. Now, obviously we have two values for k, so we're gonna have to write that, we're gonna have to adjust that accordingly. This is going to be a r root lambda plus b r, negative root lambda. And now we just want to see what we can do by applying our boundary conditions, hopefully reduce this equation to some extent. So we're going to go r of 1 is equal to a plus b is equal to 0. We have b is equal to negative a. We're going to use that to kind of rewrite our equation now in terms of only a. So, we have r now is equal to a times r root lambda minus r root negative lambda. Again, that's just replacing b by negative a. Pretty straightforward again, hopefully. And then apply our second boundary condition, r of b is equal to a b root lambda minus b negative root lambda is equal to 0. Continue to reduce this. Obviously, we can't have a does not equal 0 because then we get the trivial solution. Since a is equal to b here, if a is 0, we just get nothing. So we definitely can't have that, and we're safe to divide through by a right here. By doing that, we get that b root lambda is equal to b to the negative root lambda. Bring this to the other side, just divide through. We get b to the 2 root lambda is equal to 1. And this is really where the problem gets interesting. Obviously, all this procedure above is not the most trivial, and it's important to have gone through it before you see it. If you're seeing this for the first time, it's going to seem very weird. That's why the practice is just so important for this class. But anyway, what we can do is then just use the exponentials here. We have e to the ln b 2 root lambda is equal to e to the 2 lambda ln b. Again, that's just a property of the exponential. And then we are able to say that this is actually equal to e to the 2 n pi I. And this is actually just a property of, it's actually just a property that this is equal to 1, e to the 2 n pi I is equal to 1. And again, that's one thing that is really crucial for this problem to remember, to be able to prove that here. So yeah. Now that we're given this, obviously we can go ahead and say then that this here is equal to this. We have 2 root lambda ln b is equal to 2 n pi I. And obviously then root lambda is equal to n pi I over ln b. And then just simply enough, go ahead and square that. We get lambda is equal to negative n squared pi squared over ln of b squared. This negative, again, important to notice that we have I squared is just going to go to -1 as we square it. Obviously, I is equal to root of -1. So I squared is equal to -1. Hopefully that's familiar. Anyway, now that we have that written out, we're really able to write our full formulation of Rn of R as an r to the root lambda minus r to the negative root lambda. Just plug in root lambda here, as we did right here. We get an times r to the n pi I over ln b minus r to the negative n pi I over ln b. So again, like I said, that procedure is very tricky, and it's not trivial at all, right? Like for the first time you're going to see it, so it's important that you go through this a couple times. And in fact, we're not even entirely done with this just yet. There's still some simplification that needs to be done. So yeah, definitely have a review. So anyway, so yeah, now to further simplify this, we're actually gonna use the exponentials again here. We're gonna just raise everything to the exponential e to the ln r of n pi I over ln b minus e to the ln r negative n pi I over ln b. So obviously, yeah, if you raise everything to the exponential, but take the natural logarithm, you still have the same equivalence. And then again, if you're taking the natural logarithm of something to some exponent, you can extract that exponent as we're going to do here. A-N e to the n pi I over ln b ln of r minus e to the negative n pi I over ln b ln r. And now we want to try to realize that we're getting close to the formulation of sine here, as we have in a couple of BVPs before. One of the other ones I can think of is when we had the boundary conditions at pi for the square BVP. We did a similar transformation and solved for the sine. It's not exactly the same here, but it's good to try to make those comparisons. So here we have a-n e to the n pi ln r over ln b times I minus e to the negative n pi ln r over ln b I. And now all we have to do is really just get a factor of 2 out. But if we just simply divide by 2i here and multiply by 2i outside, we essentially get the same. Obviously, it's equivalent. We're just dividing and multiplying. But that makes it more clear right away that we're looking at sine here. So then we actually just have that Rn of r is equal to 2i an sine of n pi ln r over ln b. Again, not the most pretty formulation here, but it's the only way this problem can be solved. So we end up with this, and then we can just rewrite this 2i an as bn. It's just another coefficient that's essentially it just contains the 2i, so it's really just equivalent basically. We have n pi over ln b ln r. So that's for the r here, and we're finally done with that. As I mentioned a couple times now, it's a pretty lengthy procedure, and it's not trivial at all. There's a lot of transformations that need to be done. And if this comes up in the exam, you kind of need to know those and know them quickly enough to be able to do it without wasting too much time. So I'd say definitely review, whether it be through this video, the course pack, or whatever. Review this and try to get down as much of it as possible, and try to gain the intuition to be able to do that. But now, so the rest of this problem is a bit easier now that we have that down. That was really the tricky part and the kind of the newer part. But we're going to go ahead and just solve for the other side of the eigenvalue equation here. Straightforward enough. We had initially, I'll just show it for the sake of it. We had this is equal to lambda here. And now we have defined lambda as negative n pi squared over ln b squared. So we can just go ahead and write that here is equal to negative n squared pi squared over ln of b squared. Now this looks nasty, but if you just look at this side, it's really just same thing we've always done with sinh and cosh. Of course, we have m of 0 is equal to 0 here, so sinh is going to go to 0. And we can right away say that this is just going to be mn of theta is equal to, let's say, some coefficient we haven't used yet, cn sinh of n pi ln b times theta. Now here I said sinh equal to 0 it goes to 0, but that's not exactly clear. Basically, when we're solving for this here, we're going to get m is equal to like a sinh plus b cosh is equal to 0. And then as sinh goes to 0, it's going to imply that b, it's going to, like, as sinh goes to 0, we need to have b equal to 0 for this equivalence. And that's going to mean that a is the only like remaining coefficient. So that's what I meant by sinh goes to 0, but it wasn't exactly clear. So hopefully that makes sense now. But again, that's one of the earlier BVPs that hopefully you're familiar with by now. Otherwise, important to review. But yeah, so now that we have this, we essentially have everything we need to plug back into our initial phi here, phi of r theta, let's say phi n. We'll just write out the terms separately. We're going to, again, combine bn and cn here into dn. We'll get dn sine n pi over ln b ln r sinh of n pi, ln b theta. And again, applying superposition, straightforward enough. We're looking for the null space here, so we can look at all the solutions summed together. We have just the summation of the exact same thing, ln b ln r sinh of n pi. This should be sinh ln b theta. Yeah, so now that we have this, we want to look at our initial condition to try to, not our initial condition, but our last boundary condition. Since it's a steady state, there's not really an initial condition technically. But we want to try to solve for dn as an integral. So we're going to look at f of r here, as we had outlined above. At theta equals pi, we have phi equals f of r. So that's what we're going to do. We're going to go phi of r pi is equal to f of r is equal to summation n equals 1 to infinity of dn sine of n pi ln b ln r sinh of n pi, n pi ln b times pi. Yeah, so now that we have this, we have Sturm-Liouville coefficients. If we just look at these two terms, and we're really able to just integrate with respect to the weight function, which, like I outlined above, is 1 over r in this case. That's based on this SL form here that we wrote. Again, that's a crucial part of this problem. So if you're not familiar with the SL theory, definitely important to be reviewed. But like I said, what that allows us to do is that we can conclude that the eigenfunctions are going to be orthogonal with respect to the weight function. And that's essentially what allows us to do the following, which is to write that dn sinh of n pi squared over ln b is equal to the integral from 1 to b of 1 over r, which is the weight function w here, times this right here, sine n pi ln b ln r times f of r dr, divided by the integral from 1 to b of the weight function times sine squared of n pi ln b. Now, if this integral didn't make sense right away to you, that makes sense. But essentially, what we're doing here is we're using the orthogonality imposed by the Sturm-Liouville theorem to be able to simplify this. And I won't go through the full derivation because that would take far too long for the scope of this video. Sorry about that. But essentially what it entails is multiplying through by multiplying through by this term and then concluding that when n, like, for any n not like, how should I say this? Essentially, you would end up with like a Dirac delta nm term, which would allow you to kind of conclude that for any n not equal to m, this gives 0 by the orthogonality. And that's how we end up at this integral right here. But that's not a very conclusive definition of it, I'm sure. So definitely have a review of the Sturm-Liouville base theory, if that didn't make sense. But yeah, essentially what we get here then is we have these two messy integrals. Obviously, the top integral, we have an arbitrary function f of r, so we can't go through and solve it. But in the denominator, we actually can solve it. I assume there won't be too many long integrals like this, but if ever there is, you are kind of expected to solve them unless you have some arbitrary function here. So I'll go through it just for the sake of it, but I'm going to go quickly. So yeah, we can let n pi ln r over ln b equal to mu. D mu is equal to n pi over ln b dr over r. Dr over r is equal to ln b over n pi d mu. Then we have for the denominator 0 to n pi ln b over n pi sine squared mu. Oops. Sine squared of mu d mu is equal to ln b over n pi times n pi over 2 is equal to ln b over 2. And yeah, I went quick here, but basically these boundary conditions are based on this transformation where we can say that for r equals 1, mu is equal to 0. For r equals b, mu is equal to n pi. That's just based on this transformation of variables here. If that's not clear, just have a look. If you just go through the algebra, you'll see that that's what comes out. So yeah, once we've solved that integral, we're able to just conclude sine dn sinh of n pi squared over ln b is equal to the integral from 1 to b, 1 over r sine of n pi over ln b ln r times f of r dr divided by this right here, ln b over 2. Now, essentially, all that's left is, I guess you would bring this to the other side, and you'd be left with dn fully defined for all n. I'm not going to go ahead. I'll just rewrite it quickly, I guess. Takes 2 seconds with the copy. Basically, we get dn here then, and we'll add this term to the bottom as we're just dividing through. And this is our dn fully defined. And then we have our phi essentially complete. Summation n equals 1 to infinity of dn sine n pi ln r over ln b sinh of n pi over ln b times theta. Not my prettiest theta, but it'll do. And yeah, so again, you can leave your answer separated like this as long as the coefficients are actually fully defined here. And that should be good to go. This should be 1 to b, not a blank integral. And that's your answer right here. Again, this is for a general form where you're not actually given some function. But if you were given a function, you would have another complicated integral to solve with the probably a similar u sub to what we did right here. But yeah. So that's gonna be the end of this video. Hopefully, it gave you a better idea for BVP 13. If you have any questions, feel free to shoot me an email or whatever it might be. I guess I'll put my email right here. Or here, just let whoever's posting this video know, and they'll forward the question to me. Yeah, so good luck on your finals, and hope this was somewhat helpful for you guys. Have a good one.